Okay, so we'll move on. There is one more thing I need to talk about the probabilities of events, and that is for independent events. Okay, and then we'll talk about random variables and the binomial distribution. So, independent events. Okay, so events are independent if the outcome of one event has no influence on the outcome of the other event. Okay, events are and so we would say for events A and B, okay, they are independent if the probability of A given B is just equal to the probability of A. Okay, so what's the probability of A happening? It's the probability of A whether or not B has happened. So the probability of A given that B has happened, that's just the probability of A. So that means, that's what it means to say the outcome of one event is not influenced by the outcome of another event. Okay, and likewise the probability of B given A would be equal to what? Probability of B, exactly. All right, and so this has the side effect, or I don't know, the effect that's saying probability of A and B, which we have said is the probability of A times the probability of B given A. This will just become the probability of A times the probability of B. Okay? And then, so then this can be extended to, you know, if A, B, and C are independent, then the probability of A and B and C will just be the probability of A times the probability of B times the probability of C. Okay? And you don't have to worry about the probability of this given that, whatever. Okay? It's just that. Okay, so we'll just leave that there. And so this is, you know, like if, you know, what's the probability of flipping heads twice in a row? Okay, well, the probability of flipping heads is 0.5, so it'd be, you know, this would be the probability of heads and then heads on the first and heads on the second flip. And this would just be probability of 0.5 times 0.5, probability of flipping heads twice in a row is 0.25. Is that good? Okay, so I'm gonna now we're gonna change topics here, and we're gonna talk about random variables. All right. There is a section in the textbook called density curves. You are responsible for learning that, but I think it's simple enough that you can just read the textbook and it'll make sense. It basically just you look at the shaded area and use that. Okay. With random variables, all right, random variables, these are outcomes to numeric, outcomes to random trials but recorded as a number. Outcomes to random trials and recorded as numbers. Okay, so you know, examples of situations where we would have random variables. Okay, so one would be, you know, we pick a random person. Okay, because this is a random trial, picking a person at random, and then we record how much money is in his or her wallet. Okay, how much money in the pocket. Okay, and so the thing we're recording is a number. Okay, $0, $52, who knows? Okay, or you know, we flip a coin. Okay, and then we record heads as 1 or tails as 0. Okay, this is now a random variable because we're recording it as a number. Okay, or you know, just roll a die, record the value that shows. Okay, or you know, maybe flip a coin 10 times, count how many times it landed heads. Okay, so all of these are random variables. There's plenty more. It's just you're doing something random and you're recording it as some kind of number. Okay. Okay, and so in these scenarios, we might be curious about the mean of our random variable. Okay, so we have the mean of the random variable, and we also have the standard deviation of the random variable. Okay, so the mean of the random variable. So what is the mean of the random variable? Well, what this is, okay, is that if we were to do these random trials many times, okay, so approaching infinity, and we were to keep track of all of the numbers we got, what would be the average of all of our records? Okay, that is the mean of the random variable. So this is, it's literally the mean of all of our outcomes if we kept track of all of these after many trials. Okay, so it would be like, you know, we repeat the random trial many times. Okay, we record all of our outcomes. Okay, and then we take the mean of all. We take the mean of the outcomes. Okay, so symbolically, we don't use y bar. Okay, so the symbol for mean of a sample was y bar, or x bar if we're using x's. For random variable, the symbol is this thing. This is mu. It's the Greek letter for m. It looks kind of like the letter U with a line up in front or something. Okay, symbol is mu. We can also write the expected value of y, e of y, meaning expected value of the random variable y. And it's customary to use capital letters for random variables. Okay. Okay, and so this is the mean of the random variable. Okay, and then the standard deviation of the random variable is very similar. It's just, we keep track of all of our outcomes, and we take the standard deviation of all of our outcomes. Okay, so the standard deviation, similar concept. Okay, so the symbol there is sigma, okay? And we would say, and we can also write the square root of the variance of y. So we might write that. Okay, so again, the concept here is we have a random variable which is just the outcome of whatever we're doing, but it's recorded as a number, and then we're going to just repeat this an infinite number of times, theoretically, and then we would take the average of all of those outcomes, or we would take the standard deviation of all of those outcomes. Okay, now so one way to calculate the random variable mean or the standard deviation of a random variable is to actually go through with the many repeated trials through simulation or something like that, or actual experimentation. But of course, we have kind of theoretical rules on how to get that, and so I'm going to put up some formulas on calculating the expected value or the mean of a random variable and the variance here. Okay, so so what is the mean? Okay. Okay. So the formula for mu, or the expected value of y, this is the sum product of y times the probability of this. Okay, so what does this mean? So this means take each possible outcome y, okay, and multiply it by the probability of getting that possible outcome. Okay, and then add those up. Okay, so it's kind of like a weighted average. You can almost think of it as that. Okay, kind of like similar to a weighted average. Okay, and so that gives us the mean of a random variable. Let's talk about the standard deviation or the variance. Okay, So on the other hand, we have the standard deviation. I'm sorry, did I flip the slide too quickly? Or are we okay? Okay, nobody said anything, so we're okay. All right, so the standard deviation of a random variable, so we're going to say sigma is equal to the square root of the variance, and then so I'll define the variance here. Okay, so the variance, what was kind of our working definition for the variance of a sample? We said it was the quote-unquote average square distance from the mean. Do you guys, does that sound kind of familiar? Average square distance from the mean? Okay. Well, the same thing holds here. Okay, we're going to have the average square distance from the mean. But how did we calculate the average when we were talking about a random variable? We didn't add them up and divide by n. We did was we took each value and we multiplied it by its probability and added those up. Okay, so we're going to do the same kind of thing here. So we're going to get the quote average square distance from the mean. So we're going to take the square distance from the mean, and so we're going to start off by doing each value y, every possible outcome y, minus the mean mu. Okay, so we're going to say take each, leave some space when you're writing this. Okay, so take each outcome y and subtract mu to get the distance from the mean. Okay, and then we're going to square that distance and multiply it by the probability of that value. Okay, square the distance, okay, and then multiply the probability of getting the outcome y. Okay, and then we're going to add those up. So this is how, you know, kind of then add them up. And then so this the action of multiplying it by the probability and adding it up kind of creates this like a weighted average. So here we're basically getting a weighted average square distance from the mean. Can we see that from the formula here? I hope. Okay. All right. So let's try an actual example of this. See if we can make sense of this. It's okay. All right. So let's say I don't know. You're going to play a carnival game here. Okay.
Could you go back to the other screen? I
Sure.
just didn't copy down anymore.
Sure. Let's. How do I do this? Hang on a second. Okay.
Just take it. Thank you.
No problem. All right. Okay. So let's say we've got some kind of silly carnival game here. All right, so the game is spin the wheel, right? Okay, so this is a little the little thing that ticks. Okay, so spin the wheel. Maybe win a prize, okay? All right, so these are the possible outcomes. Outcomes are $0 prize, $1 prize, a $5 prize, and a $10 prize. okay? And what is the probability? I don't know. I have to make these up. Okay. So you get the $10 prize with 1% probability, the $5 prize with, well, I guess, I don't know. Looking at this, it's probably more than 1%. All right, sorry. I'm messing this up here. So 5% probability of the $10 prize and 10% probability of the $5 prize and 25%, so what, everything else is what, 60%? Okay, so everything adds up to 1 now, right? Okay, is that okay? Did I add this up correctly? 35, 50, yeah, okay. So what we have here is, what is the expected amount you will win? Okay, so here we're asking for the mu, which is going to be the sum of each outcome y times the probability that the random variable takes on that value y. Okay, so here the possible outcome is 0. That happens with probability 0.6. Okay. You get outcome 1 with probability 0.25. So it's, the outcome y times the probability that we get that outcome. The $5 outcome happens with a 10% probability, and then the $10 outcome happens with a 5% probability. Okay? And so your expected winnings will be 0 plus 0.25 plus 0.5 plus 0.5. And so we, over the course of time, every time you play the game, you're expected to win $1.25. Okay? Of course, when you play, you never win $1.25. You either win 0, 1, 5, or 10. But because those happen with different probabilities and whatnot, if you were to play this game, thousands of times, your average take will be $1.25. Okay? Yes?
Similar to what they did in one of the videos where they play a game about cracking an egg over your head. Is makes sense? Getting the boiled eggs together.
I don't. What video was this?
P-value guy.
The p-value guy? Oh, I don't remember. Maybe. I'm sorry. It's been a while since I've seen those videos, so I don't remember. Quite possibly. I don't know. Okay, so this is what we have for our expected value here. Is that okay? All right. Okay, and then so let's do our variance. Okay, so the variance of y is going to be the sum of each value minus the mean squared times the probability of getting that. Okay. So I'm going to take each value and subtract off the mean. Okay, so I'm going to do 0 minus 1.25. So this requires that we've calculated the mean. I'm going to square that and multiply that by 0.6. And then I take the next one, 1 minus 1.25. I square that distance and I multiply that by its probability. And so this is just a matter of punching this into your calculator at this point. And I multiply this by 0.10, and 10 minus 1.25 squared, and I multiply that by 0.05. Okay. It is interesting to note that for the mean, that single $10 prize option of getting, 5, this contributes almost, like 40% of the expected values here. Okay, so if you keep playing the game, until you hit that 10, you're not really getting what you're expecting here, or the 5, I guess. Okay, so let's punch these into our calculator, and I can just punch it exactly as I see it. 0 minus 1.25. I mean, you can do this. Some of this math you can do in your head. So 0 minus 1.25 squared times 0.6 plus parentheses 1 minus 1.25 squared. Oops, that is not the button I wanted. Squared times 0.25 plus 5 minus 1.25 squared times 0.1 plus 10 minus 1.25 quantity squared times 0.05. Okay, so I do that and I get 6.1875. So that's my variance. And so my standard deviation, sigma, is going to be the square root of 6.1875. So I just do square root of this answer, and I get 2.487. Okay, so our winnings are expected to have an average of 1.25 with a standard deviation of 2.487. Okay, so if we were to play this many times, this is what we would expect, right? So I guess 0. Something like that. Okay. Is that okay with everybody? Random variables? Yes, question.
Maybe just to clarify what it means in the real world again. So I feel like on the last one I kind of blanked. So the $1.25 is what you would expect if you play it a bajillion times.
Yeah, if you played a bajillion times and you took your average winnings, that's $1.25.
Okay, and then the 2.487 in the real world means
This is kind of your spread in the winnings. So some days you're gonna walk away with $0. Some days you're gonna walk away with 10 and
okay,
things
so
like
it's
that.
This is the
Yeah. So another game. Okay. So let me just kind of give you a sense. Let's say there's another game, a different game. Okay. All right. And in that game, either you win a $0 or you win $1,000. Okay. And then let's say the 1,000 happens with probability 0.00125. Okay. And then so what is this, 0.99875. Okay. So both of these games have an average winning of $1.25. Okay. So I mean, you could do the math, and both will have an average of $1.25. Okay. And so a casino could offer both of these games, right? And if as long as they charge more than $1.25 to play, let's say they charge you $1.50 to play, and so that would be like their cash cow because it's making a ton of money on them, right? So if they charge you $1.50 to play, in the long run they're going to make the same amount of profit for both. Okay. Which game is more exciting to play? Well, I don't know. That's actually okay. Never mind. That's not a good question to answer. Okay. Because for what's going to happen is, with this game, people are going to walk away with $1, $5, or $10 quite often. Okay. In this game, it's like almost everyone who plays doesn't win, and then only once in every so often somebody walks away a winner. Okay. And so the variance that we will see over here is going to be much bigger over here. Okay. And if we think about the spread in the winnings, either you're 0 or at 1,000, there's a huge amount of spread there, right? Whereas in the other case, you kind of have a little bit more even winnings, right? What's the most boring game? The most boring game would be you have a payout of $1.25 with probability 1, okay? It costs $1.50 to play, all right? Everyone's gonna, you won't walk away empty-handed, okay? This will have, this will be the most boring game, and sure, the casino could offer this game too, and they'll still make the same amount of profit based on each person who plays, but no one's gonna want to play this game, right? Because there's no excitement in because you know that you're just gonna, you know what's gonna happen. That's not fun, right?
Also gonna lose 25 cents.
Yeah. If they charge you, yeah, that's like. Essentially, we could turn all the casino games into this, and then everybody would be like, "Oh, now I realize I'm just throwing my money away." Okay. And this would have a variance of 0, right? This would have no variance. So we could imagine that, and that would, I mean, you could make it quote more exciting by having $1.50 versus 0, or I don't know, something, but it's just not. It's not the same. Okay, so and this was a problem that casinos were having with their. So back in the day when you had slot machines, they actually had actual physical wheels, and they would come up with these combinations. Okay, but because of the limitations of the physical wheels, the biggest jackpot they could offer was like $1,000, right? And then someone was like, well, what if we want to offer $1 million jackpot or something? Well, you would need like really, really, really huge wheels and like 50 of them, and then they were like, oh, well, no one's going to want to play that. So they decided, okay, we're going to have electronic random number generators, and we're going to have a screen that makes all these whistles and bells and noises and stuff. And then so that screen that shows up, it's really just a placebo, okay? What happens as soon as you push the button, the computer has generated a random number, and it has these payout things, okay, that decides how much money you're going to win, okay? And then what happens on the screen, it's just a placebo to match whatever number has come up and been generated ahead of time. And it's just like they purposely, they've taken psychologists and try to figure out, exactly what amount of enticement we can do, and so, they've tried to create these set of probabilities, and it's truly random. They're not rigged, and they're not like cheating you, but they're taking advantage of our feeble human psychology and just saying like, oh, flashing lights, oh, I almost won. I just have to play a few more games, and before you know, you're out $50 or something. So. Not to say, I still enjoy going to Vegas and I still play games of chance, but it's just, I know full well what I'm doing too. So, and they, so it's all of this stuff. Okay. All right. So anyway, this is what we've got. Okay, so that's what we have. Random variables. Yeah, and so the variance. This is like, what are the units on variance? It's like square dollars. I don't know what that is, okay? 6.1875 square dollars. That's, so the variance actually has some nice mathematical properties which are useful in a lot of calculations. And so when you're dealing with statisticians, a lot of times they'll talk about variance rather than standard deviations. But from a human perspective, I couldn't tell you what a square dollar is. So, certain things make sense, like a square meter or a square foot. Like, oh, that's a thing of area. Yeah, I get that. A square dollar, I don't. I still haven't figured that out. Okay. All right. Okay. So our last bit, we're going to cover the binomial distribution. Okay. The binomial distribution is a special case of a random variable. And the way the binomial distribution works, well, maybe I have to explain the scenarios in which we use this. Okay. And so what this does is, we're going to, we repeat a random trial n times. Okay. Each random trial only has 2 outcomes. And this is why it's called the binomial distribution. Only has 2 outcomes. So it's either, and in the literature we've labeled this success or failure. Okay, now these, you know, in life we associate success and failure with like good and bad things, but it's really just, did something happen, yes or no? Okay, so it's probably better off to just say yes versus no, but in the literature we've labeled them success or failure. Okay, each trial is independent of the other trials. What does it mean to be independent? Yeah, so each trial is independent of other trials. Okay, and that means, so the effect of that is that each trial will have the same probability of success p. Okay, and then and we would say we are interested in getting a certain amount of successes. And for whatever reason, our textbook uses the letter J, and I'd say most other texts use X, but for whatever reason, they've chosen J, and that's fine. Okay, so, you know, what are some examples? All right. So the simplest example is, you know, I flip a coin 10 times, okay? Each flip has a probability of heads equal to 0.5. What is the probability the coin lands heads 6 times? Okay? This would be a binomial distribution problem, okay? We're repeating a trial, random trial. We're flipping a coin n times. Okay, each random trial has only 2 outcomes. You can either get heads or not heads, all right, which we generally say tails. Every coin flip doesn't depend on the other coin flips. They're independent, so every coin flip will have probability of 0.5 getting heads, and we want to know what's the probability that after 10 coin flips it has landed heads 6 times. Okay, so in our case we would say n is 10, p is 0.5, and j is 6. Okay. All right. Maybe we can say in practice. So during practice, a basketball player will practice free throws. Okay, he will shoot 20 free throws. Okay, and this may or may not be a good assumption, but we're going to assume that the free throws are independent of each other. Okay, so you know each throw will have a probability. We'll say 0.8 of making it. Okay, and we're going to say, what is the probability he makes, I don't know, 18 out of 20? Okay, so what do we have here? N is 20, P is 0.8, J is 18. Okay? Does this make sense to you guys? Okay, so how can we answer these questions, all right? Or, I'm sorry, did I flip again too quickly there? Just a second. Okay, let me flip back for you. Yeah, no problem. Okay, so let's start off with an easier example. Okay, so we'll say simple example. Okay, so this time let's say I have I don't know, some kind of funny coin. A funny coin has will land heads with probability 0.7. Okay, and I'm going to flip this. I flipped the coin 4 times. Okay, all right, and I want to know what is the probability I get, we'll say 2 heads. Okay, so if I get 2 heads, how many tails do I have to get? 2, right? So 2 heads also implies and 2 tails, right? Okay, so I'm gonna just build a crazy tree. All right, so on the first coin flip I can get heads or tails, and on the second coin flip I can get heads or tails, and on the third coin flip I can get heads or tails, and on the fourth coin flip I can get heads or tails, right? Okay, so I'm just kind of building this tree out, and I get something crazy like this. And I don't feel like labeling all of these. Or maybe I will. I don't know, it doesn't matter. Okay, but all of these, what's the probability of getting heads? It's going to be 0.7, and the probability of getting tails is going to be 0.3, right? Okay, and then so all of these will be 0.7, 0.3, 0.7, 0.3, okay? And so, you know, this is a lot of work, right? Okay, so I want to get 2 heads and 2 tails. So I'm going to list out all of the possible ways I can get 2 heads and 2 tails, right? I'm going to just say I'm going to get heads, heads, and then I have to get tails and tails, right? So one possible way will be heads, heads, tails, tails, okay? Another one could be heads, then tails, and then heads, and then tails, right? So I could go heads, tails, heads, tails, and then I could also get heads, tails, tails, heads. Okay, so I'm not even gonna, I'll just tell you what else I can get. Okay, I can get tails, heads, heads, tails, tails, heads, tails, heads, and I can get tails, tails, heads, heads, right? So these are all the ways I could get 2 heads and 2 tails if I flip the coin 4 times. Okay. All right, let's let me copy this over to our next page. Okay, so what's the probability that I get heads, heads, tails, tails? Okay, so the probability would be they're all independent, right? So I'm going to do 0.7 times 0.7 times 0.3 times 0.3. Is that okay? All right, and then heads, tails will be 0.7 for the heads, tails will be 0.3, 0.7 for the heads, and tails will be 0.3. Okay? Now, if I look, I can just say, oh, this is 0.7 squared times 0.3 squared, right? And then the same, if I just rearrange terms, this is also 0.7 squared times 0.3 squared. Okay? And all of these will be 0.7 squared times 0.3 squared, right? Because if we look, they all have 2 heads and they all have 2 tails, right? I should just. They all have 0.7 squared and 0.3 squared. Okay? So the total probability will be 0.7 squared times 0.3 squared. And how many different ways, arrangements are there? 6 of them. So the total probability would be 6 times 0.7 squared times 0.3 squared. Is that okay? Because we want heads to happen twice, right? So we got heads, and then tails, and you know, any arrangement of these, I'm going to have heads happen twice and tails happen twice, all right? And I've got just 6 possible arrangements. So this is what we have, okay? So basically, this is number of arrangements okay, and this is times. What is this? This is probability of success raised to the number of successes. So I need to get 2 heads, right? So if I'm flipping the coin 4 times, I need 2 heads, which means I also need 2 tails. So I'm going to have probability of success raised to the number of successes times, and what's this over here? Probability of failure raised to the number of failures, right? Is that okay? Okay. So when we create the formula, okay, I'll get to the number of arrangements last, but I'm going to have the probability of success. So if I want the probability that our random variable y will take on j successes, okay, so this is the probability of getting j successes. Okay, we'll get to the number of arrangements in the end, but I've got p, and I want, if p is the probability of success, how many successes do I want? I want j of those, right? Okay, and then we have a total of n trials. Okay, so we have j successes in n trials. Okay, so what's the probability of a failure? If p is the probability of success, probability of failure is 1 minus p. Okay, and if I have a total of n trials and I want j successes, how many failures am I going to have? N minus j. Okay? So I want probability of success is p. I'm going to raise that to the j power. Probability of failure is going to be 1 minus p, and I'm going to raise that to the n minus j power. And all I need left is the number of arrangements. Okay? And so I'm going to just write that here. That's going to be n over j. This is read as n choose j. It can also be written n cj. This is the number of arrangements for j successes in n trials. Okay, and this is p to the j times 1 minus p to the n minus j. This is the same thing that we had before. Probability of success raised to the number of successes I want, and this is probability of failure raised to the number of failures I need to have. Okay, so n choose j, this thing, the formula for this is this. I would just say your calculator probably has this button on there, and just use that. For example, if you were going to flip the coin 10 times and you want 5 heads, you would do 10 choose 5. And so on your calculator, you probably have an NCR button. And you might have to, depending on your calculator, you might have to hit the math button or a probability button, or you hit the math and then you use the menus to go to probability and you find NCR. I don't know. Or you might just have the NCR button. So on my calculator, it's over the division sign. And so I would do 10, and then I would hit shift, the divide button, and 5. And I hit equal, and I get 252. Okay. On your calculator, you might have to hit 10, math button, find NCR, or under the probability menu, find NCR, and then you hit 5. If you're having trouble with this, you can come see me and I'll show you how to do it on your calculator. Okay. Otherwise, you'll need a factorial button, or you're going to have to do a bunch of legwork and do like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 or something. Okay. All right, is this okay? Or maybe your textbook, I think the 4th edition of the textbook has a binomial table in the back, and you can look it up there also. All right, is this okay? All right, so let's try one of these problems out. Okay. Okay, so let's. I'm going to just scroll back up, and I will copy this basketball player problem. Okay, so if you have this already written in your notes, you can just say like the basketball player problem. Oops. Okay, so we're gonna try the basketball player problem. Okay. So in practice, a basketball player will practice free throws. He will shoot 20 free throws. Each throw will have a probability of 0.8 of making it. What's the probability he makes 18 out of 20? Okay, so I'll give you guys, I'll pause the video here, and I'll give you guys a few minutes to figure this out. All right, so this is a binomial problem. We've already labeled n, p, and j. All right, and so what we want is I'm going to have 20 choose 18, right? This is the number of arrangements I can have 18 baskets being made out of 20 attempts, okay? And then, so what's the probability of a success? It's going to be 0.8. And how many times does the success have to happen? 18 times. So it's going to have 0.8 to the 18. What's the probability of missing the basket then? 0.2. And how many times is that going to happen? 2 times. Okay? So I've got 0.8 raised to the 18 and 0.2 squared. Okay? Times 20 choose 18. So 20 choose 18 is 190. And I'm going to just do 190 times 0.8 raised to the 18 times 0.2 raised to the 2. Okay, then I just punch that into my calculator and I get 0.1369. So 0.8 to the 18 times 0.2 squared, 0.1369. And that's my answer. Okay. Where did the 190 come from? That came from 20 choose 18. So on my calculator, I just did 20 shift choose 18, and it spits out 190. So this is 20 over 18. I mean, we could do 20 factorial over 18 factorial times 2 factorial, and this would be kind of a lot of work. It would be 20 times 19 times basically 18 factorial, right? And then on the bottom I have 18 factorial times 2 factorial, and so these cancel, and then I have 20 times 19, and then 2 factorial is just 2 times 1, and so the 2 and the 20, and then here I get 10 times 9, there I get 190. Okay, so you could do it that way, but it's easier to punch it in your calculator. Okay? All right, so we have this, all right? I could just ask, what is the probability the player makes at least 18 baskets? How do we answer at least 18? So here, n is still 20, p is still 0.8, but j is now equal to 18, 19, and 20. Okay? All right, and so here I have the answer to 18. I have the probability that y equals 18 to be 0.1369. Okay? And then so I would have to calculate probability that y is equal to 19, and I would have to get probability that y equals 20. And then I would figure these numbers out, and then I would add those add those three numbers together. Okay, so add these together. To get our answer. Okay? And I don't feel like doing that right now, but I hope this just illustrates what you would need to do if the question said something like at least 18, right? So at least 18 means 18 or more, 18, 19, or 20. Okay, so sometimes you might see language like that in a problem. Okay? We could figure out the entire table of probabilities, right? So if we're taking 20 shots at the basket, there are potentially 21 possible outcomes, okay? The player can make anywhere from 0 to all 20 baskets for a total of 21 possible outcomes. So we could have a table of all 21 possible outcomes. I would not make you do that. That would be way too tedious. And we actually have computers to do this kind of grunt work for us. But, you know, if we had to, we could make a table of all 21 possible outcomes. Okay, and that would be, you know, anywhere from 0 successes to 20 successes. Okay, so, you know, n trials, you're going to have n plus 1 possible outcomes. Okay, if we wanted to say, okay, this guy, we're going to keep track of this guy over his whole life or whatever, I don't know, this actually wouldn't work. But we could say, you know, what is the mean number of baskets he will make? Okay, here we're basically asking what is the expected value of y, or what is our mu, okay? And in this case, we could go through all of the work of, you know, the weighted average. For binomial answers, for binomial random variables, there's a shortcut, n times p, and I think this is rather intuitive, right? If he takes 20 baskets and each basket has a probability of 0.8, we expect 16 baskets, okay? So that's the expected value there, n times p, 16. Okay. The standard deviation, this is a little less intuitive. This is going to be the square root of n times p times 1 minus p. Okay, and so this becomes 20 times 0.8 times 0.2. We get the square root of 3.2. What is that? Mm, 1.788. 1.789. Okay, and so this is just a measure of the spread in the number of baskets the player will make. Okay, so we're expecting on average that he'll make 16 baskets with a spread or a standard deviation of 1.8 baskets, really. So maybe some days he'll make more than that, some days he'll make less than that, but we're expecting, you know, this is kind of the measure of spread for this player. Is that good? All right, we'll end there. You guys have a quiz next week, so there's some information about that posted, and I think we'll be okay. Yeah, question?
I remember reading that we're allowed a note card on specific exams.
Yes, yes. So yes, next week you can have a 3x5 note card. Okay, please either buy yourself 3x5 note cards, or if you're gonna cut a piece of paper out, make sure you use a ruler and that it's 3x5. Okay, I don't want to be the bad guy, but if your paper is bigger than 3x5, I have to take it away. Okay, just
I have to ask, but is it one-sided, two-sided, handwritten?
double-sided, and whatever you put on there is fine.
Thank
Okay.
you.